Okay, guys, we'll now proceed with some alternative procedures on how to deal with slot design and analysis beyond the elastic range. Okay, so we are talking here the plastic analysis or the linear analysis, which has something to do with the non-linear range of response of slabs if in case the uh, working loads are exceeded uh, by a way of introducing load factors, okay, in theoretical uh, in theoretical aspect of the analysis. The yield line method is one of the a few approaches that we can rely on, especially on irregular panels. Okay, so we will be exploring um, strength and advantage of the analysis for irregular panels. So the basic assumptions are: one, material is elastic, perfectly plastic. When the moment of curvature is also within the bounds of an elastic plastic range. So the maximum load corresponding to the load at which the structure degenerates into a mechanism is actually an upper bound here. Okay? So the U-line analysis, as we have uh, discussed previously on our first lecture here, uh, is actually on the upper bound. Here. Okay, so let's now talk of some fundamental principles of the method. We take note that we are talking here of a mechanism upon which the slab system, undergoes a deformation without any application of additional load, wherein that mechanism will dictate the failure mode condition uh, inherent within the system. Okay, so if we draw now a stress strain uh, scenario that defines elastic perfect plastic. Okay, so when you see this graph, we are defining an EPP or elastic perfect plastic uh, stress strain graph. Okay, upon which, of course, this only happens when your material exhibits the property of the P. So converting this into a moment curvature relationship, we can now therefore introduce the nonlinear moment response in terms of curvature or rotation in this manner. And basically, the range of activity that we're talking here, starting from the yield curvature up to the plastic behavior that we're talking about, is four times. Okay, so this is one, two, three, four times this yield curvature. For the stress distribution, so this is now the internal stress distribution that we normally use, no? In an EPP, an elastic perfect plastic material. So this is the limit upon which your material can only give you a maximum of Fy, okay, as your yield strength. Okay, if it's an elastic perfectly plastic material, then you cannot go beyond the yield strength. Rather, the formation of the plastic hinge will develop a redistribution of uh, yield curvature from the extremmost fiber, gradually shifting towards the neutral axis until it reaches what you call a plastic hinge. Okay, the development of such plastic hinge will start when your Fy theoretical has been exceeded by the stress starting from the extremmost fiber. So you may now define your plastic modulus as equivalent to zero in this stage. Okay, so at this stage your E plastic becomes zero, and the definition of your hinging will be from the extremmost uh, fiber, okay, going towards the neutral axis. So this is now an elastoplastic behavior, or it's in between the elastic range and the plastic range of this box. So for the moment curvature relationship assumption or representation, it can be represented by this slope. Okay, so EI is the flexural rigidity. Therefore, the slope defined by connecting a point on the yield line and a point somewhere at 4 times your Phy defines your bilinear representation of your moment curvature in this regard, and upon which the plastic moment now, okay, is computed on the basis of this uh, 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 property defined by the slope of this second line. Okay, so somewhere here will be your plastic moment ME, which is of course greater than your ME. So the mechanism for a flexural member, we are talking here of a beam. Remember that the principle that I just discussed is applicable to any element or member that is capable of exhibiting flexural bend. So for a continuous beam, the mechanism, when I talk mechanism, I'm talking of the behavior, okay, the failure behavior or the collapse behavior that is expected of your system. Okay, so in terms of continuous beam here, uh, we are to, since these are separately connected uh, and uh, externally independent to each other, then we can talk of local failure mechanism that has that is very similar to a simply supported beam system. So if the degree of indeterminacy for one local beam span is uh, uh, 0, so there's a 0 degree of indeterminacy. You only have to have at least one, okay, plastic hinge to be formed. In case this is not externally separated, or in case this is internally or externally rather connected to each other, these two beams are externally connected, we can say that this has a degree of indeterminacy equivalent to 1. So if I add 1 plus 1, my number of plastic hinge will simply be equal to 1 DOI plus 1. So this is now equal to 1 plus 1 equals 2. So I will consider now these two hinges as my plastic hinge. Okay, and this is a natural hinge or a real hinge. Okay, so this is a real hinge and this is a plastic hinge. So it depends upon your interpretation of the external connectivity or external boundary condition in terms of your support upon which your number of plastic hinge formation may be determined. So these are all possible local mechanisms that we can expect uh, that we may expect to happen in terms of the failure of the system. For a portal plane, the same is true. So the number of plastic hinge is equivalent to the degree of indeterminacy n plus 1. So if I have here my degree of indeterminacy, which is 3, so I just add 3 plus 1, so this is DOI, okay? So 1, 2, 3. So I may have only I only need rather to have 4 plastic hinges to make this system fail. So this is as far as a portal of frame failure is concerned. For a beam failure, local, okay, so if I have here a local beam failure, so I have a DOI equivalent to 2 at this point, okay, and then if I add 1 plus 2, I can have my number of plastic hinge equivalent to 3. So I have 3 plastic hinges there. Here, the number of plastic hinge is 3 plus 1, so this must be 4. Okay? And so is true with another another type of failure, which is a combined. So this is a portal failure, local beam failure, and this is a combined beam and portal failure. So if I consider the total number of degrees of indeterminacy equivalent to 3 here, my number of plastic hinge will simply be equivalent to 3 plus 1. So I may count 1 and 2 here, and I only need 2 more here, either this or that, to make this frame unstable and uh, and it will be subjected to a failure mode as soon as these four plastic hinges were developed. For a gable frame, it's actually similar to a portal frame. The only difference that your beam here is now divided into two gable uh, rafters. Okay, so you only need 1, 2, 3, 4 for a gable type frame. So your NOPH here is 4. So for a local gable rafter failure, you only need 3. NOPH equals 3. And here for the combined, we have again 4. So it's very much similar to the failure mode of the system of the previous system, which is a portal frame. So the technique on how to get the capacity, okay, of the system is you analyze and solve for all the possible mechanisms and then choose the smallest WP that will trigger the weakest, okay, the weakest uh, mechanism for a particular frame system. So let's have an example here of a prop cantilever. Uh, so for the prop cantilever, we actually have, or we actually know the elastic, okay, the elastic moments that we need at the maximum critical points, which are of course somewhere here within the span and somewhere here at the fixed support. Okay, so this is a real hinge. So what we expect here is to create a plastic hinge, or to form a plastic hinge at the point very near these critical points or critical sections. And using elastic methods, we can simply solve for the reaction at point P by this formula. Okay, so if we know what is this moment and we name it as your plastic moment here, elastically your RB here, by taking summation moment at the fixed support equals 0. So if I take moments at the fixed support, okay, 0, then I can have this as my equation. Okay, so this will be empty all over the length, and then WL over 2. Okay, so multiplied by this is WL L over 2. And of course, this is RBL. You simply cancel out your 1L there. It becomes WL L over 2. Okay, so let me show you the detail of this. So it's simply equivalent to RB times L is equal to, of course, you have here a, a counterclockwise moment. So if this is again a counterclockwise moment, this will be negative. Okay, so it's negative NP. Okay, so RB negative NP, and this is a clockwise moment, so this will be plus WL squared over 2. Okay, so if I solve for RB now, I will simply have WL over 2 minus NP over. Okay, so this is based on, of course, elastic theory. So for the moment at a certain point x that we assume to be unknown, we can just make use of same system and solve for mx in this regard. Of course, we have to change your L into an x to make the equation in terms of x. Okay. So for the derivative, so if we differentiate this moment, we are now getting an optimization procedure. If we want to optimize the moment by simply differentiating this with respect to x and equate to 0, we are just making use of an optimization technique. So we will come up with x is equivalent to xm, the location at which your x will have a maximum value. Sorry, your m will have a maximum value. So xm will actually be equivalent to this one. So if we set mx equivalent to mp and solve for wp, we will gain a value equivalent to this. Okay, so this is now the plastic moment that we need. Sorry, the plastic load that we need to allow your beam to have a plastic moment equivalent to whatever m is that. So your W is dependent on your plastic moment. So this plastic moment is simply the plastic capacity that we can compute if we have designed this beam using elastic procedures. Okay, so we are now talking here of capacity limits in this regard. So that's how we deal basically on the limit analysis. And if we are going to compare, okay, the value of your W in terms of elastic, we can actually see that there's a slight, okay, W elastic has somehow has a different, okay, value compared to the plastic load, the ultimate load that we talk about here in this. Is it greater or less than? What do you think? So expectedly, your elastic must always be less than your plastic load. Okay, because we are talking here of an upper bound theorem, in this regard. We expect that your computed load in terms of limit analysis will always be less than, greater than rather, than your load at service. Okay, so I will be giving you the other approximate procedures, or explaining to you some more procedures on this on my next video. Uh, at this point in time, thank you for listening and have a nice day.